Hello, everyone. I'm Michael Tellerman from Volkswagen Group of America Innovation Center, California. And I'm presenting, is fair AI possible? Answer is yes, and we have all we need for it. The AI technology is a great amplifier. It's scaling up both achievements and deficiencies. So obviously, because it's software, it's repeated everywhere, and it will be proliferating to everywhere in society. Everyone will have interaction with it, and already have now. So what is artificial intelligence? In a nutshell, it's a human-built machines that's capable to compute predictive models. So it's basically about prediction. And the core of artificial intelligence, ability to learn from data. So we're learning from existing data and we're trying to predict something unknown. Because of that, properties of the data and how these algorithms learn it will completely define the outcome. The root of any unfairness, because of that, is bias in data. So if you look at what we have, everything is biased. People have biases. Data have biases. Algorithms have biases. And artificial intelligence decisions or predictions have biases. Now, how we know that it's unfair? I mean, personally, every time we feel something wrong, we can understand that this is unfair. But how we understand the unfair for every one of us? The outcome of algorithms is unfair and biased when it contradicts our social norms or our laws. So what it really means, it's up to us to decide what is unfair. Algorithms itself doesn't have any fair or unfair built in. You cannot derive from this algorithm what's supposed to be fair and what's supposed to be unfair. It's always up to us. So now let's consider examples when we have bias in data and how it will affect AI solutions, how that really happens. So of course, all the data that we have natural biases. Let's consider this example when we have lots of images collected, I don't know, from internet or somewhere. And for some reason, we have these images of cats and dogs. For some reason, we have 99 cats to one dog in this image data set. So that means it's unbalanced, it's biased. I'm not sure about real data set of that. I just like dogs, so and I have some in rare. So what we will have as a result of that? If we have just very naive primitive classifier that will always predict cat for any given image, that will result in very respectful 99% accuracy. See? So it doesn't matter what image is, it will always predict cat, and it's almost always right. And of course, we feel that something wrong with it. For example, if you take just single image, and what you want from that image to predict what it is, and for that image either wrong or right. So for particular image, it's basically 50% accuracy. Of course, what it means, we want to have test data or prediction data that consider each data point equivalently and have the same accuracy for everything. Okay. Of course, if you're using this biased data set, for example, for pedestrians, and it has 99% accuracy, it's really bad. It leads to disaster. So why this naive approach is wrong? Because we need to look beyond training data set. The problem is that training distribution is different than test distribution. The thing is, we want to train on available biased data, and nevertheless, we want to have equally accurate prediction for every test data sample. And this is, of course, very different what we have in training and what we want in test. The solution that I will consider here called Bayesian importance sampling. So to go to that, we will define a little bit what is Bayesian in a few very brief definitions. What is Bayesian learning? So we're defining family of models, and very often it's continuous family of models. Then using these models, we can compute probability of data for each model. That's conditional probability of data for a given model. Then we can use Bayes' theorem to find probability of model for this data, given this data. And of course, if you know probability of model, every model that we consider, we can compute probability of new data, just averaging predictions for all the models. That's, in a very brief definition, how Bayesian learning works. Now the question is the following. We have data set. Should we use all the data that we have? If you look how we're collecting data, that happens pretty much randomly. That means, for example, we're collecting data on certain days, and then we're deciding to stop because we have limited budget, because we don't have time, because we think that it's enough data to work with. But if you collect data for another day, if you collect more data, it will be different data set. If you collect less time, you will have different data set. So data collection gives us, there's no ideal data set. We're always collecting something that we can. And that means this data would be depending on how we're collecting and how long we're collecting and all this. Second thing that we have to consider, that everything that exists in data will be learned by our algorithms. So if data non-perfect, deficient in any way, that deficiencies will be learned. So what will happen if we select some subset of known data? So of course, for that subset, we will find new solution compared to all the data. The problem is, for every selection, the solutions that we will find would be different. And whatever we select, as many selections we can have, we can find as many solutions. So how we can deal with that? The solution to that problem would be to find selection in our training data that will correspond to distribution of test data. And this is what we have Bayesian importance sampling. So the critical part of that is to define unbiased validation data set, where we have all data balanced, all data trusted, all labels correct, that we can verify that. And size of that data set could be really small. It's just representation of what we want. Then we have algorithm that will learn solution from training data and will select data points from our training data set that contribute to correct predictions in our validation data set. And the rest of the data would be unselected, thrown away. So specifically, how that works? The sequence is the following. We have to define unbiased validation data set. And this is exactly where we declare or implement our social norms, laws, and our understanding of fairness. Then we find solution and selection from training data that give us correct predictions for unbiased validation data set. And finally, the found solution will be free from original biases. The same approach can work for correcting wrong labels, because if label is wrong, that means that data point will not contribute to right solution and will not get selected. Okay. And this approach gives us interesting results. We can assign some importance factor to each data point. So if importance is 1, that means that point is selected. If importance is 0, that means that data point is excluded. So practically, that importance factor is just multiplier for the loss of each training data sample. What we will find that this importance completely depends on correlation between training data sample and validation samples. If it's positively correlated, we're getting high importance. If it's negatively correlated, we're getting low importance, and practically it's excluded from training. Exactly the same approach would be used for more complicated case, something like semantic segmentation. So in this case, what we have prediction for every pixel in image, right? For example, we're trying to predict where people in this image. So we're classifying each pixel as something that belongs to people, something that not belongs to people. Of course, if you look on this data set, it's very highly biased, because number of pixels that belongs to people is very small, much less than 1%. And we can use importance sampling per pixel to predict correctly data, to learn solution from this data and predict that consistent with validation data set that we can define and check. This is resulting outcome after 200 epochs when we train with importance sampling. So on the left top you see original image, on the right top you see ground truth, and on the right bottom we see predictions that's already obtained at this point. And on the left bottom we can see importance map. So white area is where high importance pixels, black area where we have low importance pixels. For comparison, if you look on training without importance sampling, for the same image, we can see result after 2000 epochs, exactly the same network. Everything is the same, just no importance is used. That means everything is equally important. We can see much longer training that produce much less accurate result for this semantic segmentation. And finally, we have a conclusion. Conclusion is that AI technology is only an instrument, and it's up to us to define what is unbiased and what is fair. Using the algorithm based on Bayesian importance sampling is very effective method for removing these biases in data. It works well for cold data samples level, like classifying different samples, or at pixel level, where we can predict each pixel, like for semantic segmentation. And finally, that approach allows us to solve problem of very big, large data set. If you have data that's accumulated to very big amount, we can always select most significant data, most important data that would be much smaller, and this is only data that we need to make right predictions. The same is true for correcting labels. We can correct labels using this approach. And that's all. Thank you very much for listening my presentation, and I'm ready to answer questions if you have it.